Hey everyone, I'm Yannick, a co-founder and core developer at Elusive, and today I'll be talking about building the future of privacy and compliance. Elusive is Web3's universal encryption layer offering both on-chain privacy and confidential computing, and I'm very excited to have the opportunity to share one of our latest big innovations with you today, which is Project Zeus. And this will change the way we think about on-chain privacy and compliance. So let's get into it. Let's start by evaluating why do we need on-chain privacy in the first place. As all of you are most likely familiar, blockchains like Solana by default are fully public, fully transparent, offering almost no privacy guarantees besides pseudonymity. And on top of that, we have a large industry of players even working on linking wallets and removing this pseudonymity. If we look at traditional finance, the system we sought out to replace, everything there is being executed on private ledgers. Hence, we have a system that is opaque, and the only restrictions to privacy there are mostly record-keeping and reporting requirements of those financial intermediaries, which leads us to a problematic situation in which actors, be it individuals or organizations, that want to move their activities on-chain have to risk the exposure of sensitive information. So what is on-chain privacy and how can we create that? Basically, privacy would be the union of confidentiality and anonymity, meaning that details in a transactional interaction remain private, and also the entities involved can have privacy. We are able to implement that utilizing zero-knowledge proofs, which basically is a cryptographic primitive in which one party, the prover, is able to convince a secondary party, the verifier, about the truth of some statement without having to reveal the statement itself. And when we apply that to blockchains, what we usually do on a public blockchain is we implement a shielded pool. And a shielded pool basically means that users are able to enter that shielded pool with their assets, and then once they're in that shielded pool, which you can think of as a single account in which every single user commonly stores their assets, those users using a different virtual ownership representation can have fully private transfers and at some point exit and enter that shielded pool again. So using shielded pools on-chain, it's possible to gain perfect privacy, which comes with another caveat, because if we look at this statistic, for example, from the Chain Analysis 2023 Crypto Crime Report, we can see that in 2022 alone, there were 23.8 billion US dollars of illicit funds, representing a staggering 68% increase from 21. So that is an issue, and what's important to realize is that having full privacy guarantees using zero-knowledge proofs and no regard for compliance risks escalating this issue. So in the past, there have been different approaches to resolving this problem. The first approach would be implementing discretionary compliance measures, which basically look like the user being able to manually give third-party access into their private data, utilized by adding viewing keys to the shielded pool. This, of course, is unable to combat illicit finance and can be used in scenarios where the user explicitly has to share some data with, let's say, tax authorities. The second approach, and a very recent approach, is this deposit and withdrawal screening, and how that works or rather the idea behind that is having a shielded pool. One might want to keep all illicit actors out of that pool by preventing them from even entering the pool. So how that has been utilized in the past was to add blacklists to those programs and then check the wallets that attempt to deposit funds against those blacklists. Withdrawal screening, on the other hand, attempts to unshield the identity of an illicit actor that attempts to transfer inside of a shielded pool or exit the shielded pool by requiring that user to generate a zero-knowledge proof to be not contained on such a list. Those approaches suffer from multiple problems. The first problem is that illicit actors on the blockchain will most likely be faster than any blacklist can be updated. And the following consequence is basically that such a system will lead to an inherent centralization effect, because we have those rapidly moving illicit actors and accordingly need to speed up those blacklist update processes. And one recent example of such an architecture would be privacy pools, in which the user, instead of having to prove to not be contained in a single blacklist, could select from different association sets that have been generated by different third parties. Now let's look at an example why deposit and withdrawal screening is so problematic. Here we have a real-world example of how illicit finance on the blockchain can look like. That's not your typical on-chain hacker that exploits a protocol. That's basically drug cartel actors using the blockchain to move illicit funds. Now if we go into an example scenario, we will look at a single week and we say on Monday some illicit activity has taken place and 1 million USDC is the output of this illicit activity. If we assume that on Tuesday this illicit activity has been identified on-chain, deposit screening will prevent on Wednesday this actor from actually being able to deposit those funds and then privately move them to whatever place they please. A second case would be identification happening after the actual deposit. In that case, withdrawal screening is working. As you can see here, the user withdraws in 4 different tranches their assets out of the shielded pool, but all of those assets can be directly linked to the illicit actor, because through withdrawal screening, the user is forced to reveal their identity. Those cases are rather unlikely. The most likely case is this one, in which the identification happens, let's say, 1 week after the actual off-chain illicit activity has taken place, resulting in the user, the illicit actor, being able to move all of their funds out of the shielded pool before any possibility of catching them. This is very problematic, because if we imagine that such a protocol, let's say, has withdrawals over 100 million USDC over the span of this week, we come to the following scenario where we say, okay, all assets that have left the shielded pool over the span of this week now might have to be viewed as tainted, because it's impossible to know if funds that have left this pool are illicit or not. The alternative scenario would be, we say, okay, there has been illicit activity, we didn't catch it, but we just need to accept it. So the illicit actor got away. Regulators will choose option 1, and also for us, in our decentralized communities, I guess it's undesirable to let those illicit actors get away, I would say. So it would be nice to find a solution for that. Deposit and withdrawal screening aren't those solutions. Centralized compliance also is not that solution, simply because that would put us back to square one, solely relying on some centralized actors to perform KYC or give such a centralized actor some reading access to private state cannot be the solution. So that's why we sought out to develop SUSE, which stands for Zero Knowledge Encrypted User Safeguarding. And the base assumption that we have is that it's impossible to keep all illicit actors out of such a shielded pool, as I just outlined. And in consequence, the goal then has to be to disassociate those illicit actors retroactively, because that's the only way of adding any safety to the honest users. In the past, it has only been possible through centralized approaches, and now I will outline how we achieve that in a decentralized way. So, first off, we start by turning our private transactions into encrypted transactions. That basically means that when a user transfers inside of the shielded pool or exits the shielded pool with a zero-knowledge proof, the user is required to add an encrypted message, which is being stored on-chain. And inside of that encrypted message, the transaction details are being encoded, and the encryption is being verified using a zero-knowledge proof. Now, the second step is we need some way of handling this encrypted state. That way cannot be any centralized actor. So what we do instead, just as we usually do when designing blockchains, we replace central entities with a distributed network. So that's what we are doing. So we have our own network, the Zeus network, which in itself isn't a blockchain, but rather a computation network that takes blockchain state from Solana as input data and output state that is then again being written back to Solana. So in order to bootstrap that network, we utilize a distributed key generation protocol, which equips every single node in that network with a key share. And all of those key shares, or rather the threshold of those key shares put together would form a virtual private key that actually never exists and should never exist, and a corresponding public key. In order to ensure that this private key is not being reconstructed, we set the threshold to be as high as possible, as close as possible to the total size of the network we have. And this public key then can be used to encrypt all of the transactions, and we repeat that process in regular intervals, the so-called epochs. And at the end of every epoch, all nodes destroy their key shares or are, according to the protocol, tasked to destroy their key share. And a new DKG is being executed, allowing the network to reconfigure as well. Now, what happens next? We have this network with key shares that collectively, as a whole, as a threshold, would be able to decrypt transactions that have occurred in a given epoch. We want the network to be able to find those transactions that have been performed by illicit actors. So what we need is some way of computing on the encrypted state and only reveal information about the encrypted state if certain conditions are met. And for that, we utilize multi-party computations. In our case, we use a protocol called Speeds, which comes with the desirable property of having the dishonest majority trust assumption. What it means is that in our Zeus multi-party computation, we only require a single honest participant in order for the protocol to perform correctly or not, to prevent an incorrect execution of the protocol. If we compare that to Byzantine fault tolerance that we see on our normal blockchains, we don't require at least or more than half of the nodes to be honest. Instead, we require one node to be honest. Now, if we assume illicit actor identification, which in the most simple case would just mean the network, the threshold of the network agrees that some actor is an illicit actor, we can now perform transaction decryption by executing such a multi-party computation into which each participating network node inputs their key share inside of the multi-party computation, homomorphically encrypted those key shares are being put together and then being used to encrypt an individual transaction. And in case an illicit actor has sent a transaction, a corresponding result is being yielded and put back to the Solana blockchain. And now everybody knows that this transaction that has happened in the past actually has been performed by an illicit actor. Our protocol additionally comes with cheater and non-participation detection, which we achieve by basically modifying the MPC protocol we use with commitments and then using those commitments and posting them to Solana, and at the end of the computation being able to verify that the computation has been executed correctly. The added benefit of that is that we can now, with this setup, turn our computation network in a sort of autonomous machine that is forced to continuously compute, continuously run those multi-party computations and identify illicit actors, because our network isn't its own blockchain. It settles back to Solana, and then on Solana we can implement staking and slashing mechanisms if any node would not participate correctly. Here's a scheme where on Solana we have different programs. One program is the shielded pool program, and then we have two more programs, the multi-party computation program and a voting program. And what's interesting here is that we are able to differentiate between the multi-party computation and voting. And voting means deciding who is an illicit actor. We can do that because our network is forced to run those multi-party computations correctly, forced to find all transactions that have been performed by illicit actors, and are forced to that by us settling back to Solana. And if this execution doesn't occur, slashing would occur, which is very powerful because now we can have a dedicated distributed voting process. We can make that a thorough voting process that utilizes third-party compliance oracles. And since time isn't of essence for us, since in any case we are acting retroactively, we can have high consensus requirements and make this process of actually outcasting someone from the privacy set as an illicit actor difficult, and add accountability to that. Let's go back to the original example. So if we now compare what we can achieve with deposit and withdrawal screening versus what we achieve with SUS, it's evident that SUS is very powerful, because what we are able to do is we are able to link the initial 1 million illicit USDC to some other 1 million USDC that at some point during the week have exited the pool, and all of the 99 million honest user funds are not tainted. They are completely separated from the funds the illicit actor attempted to move through the protocol. So in essence, this multi-party computation-based compliance mechanism is very effective at combating illicit finance, and we can implement a decentralized and thorough decision-making process, which wouldn't be possible if we had to prevent illicit actors, which in the moment we didn't even know are illicit actors, from doing something with our protocol. And we have multiple steps in place to minimize trust and enable self-regulation in this protocol, ranging from epoch-based key destruction to having large thresholds to utilizing a protocol that comes with the dishonest majority trust assumption. All right, that's it. Thanks for your attention. If you're interested in what we are building, you can find us on Twitter at @elusiveprivacy. We will, in the next weeks, release our white paper detailing all of the cryptography and distributed system design behind SUSE. Thanks for your attention.